Now we're going to look at relative alkene stability. We can calculate delta H from the bond dissociation energies, DHs. Delta H is calculated through bonds being broken minus bonds being formed. And if the bonds being formed are greater in energy than the bonds being broken, then the reaction is going to be exothermic and it's going to be negative delta H. And obviously the math on that one makes sense. Exothermic means the K equals is greater than 1, meaning the products are favored, which also makes sense because if the energies of the bonds being formed is greater, then obviously the products are going to be favored. However, delta H is used to approximate whether a reaction has a favorable equilibrium constant, but if precision is needed, then we use delta G. So alkene stability, right? Catalytic hydrogenation is the addition of hydrogen to an alkene to form an alkane product. It is going from ene to ane, right? The process requires a catalyst, palladium on carbon, PD over C, the addition of hydrogen to a carbon double bond to form a carbon single bond. Now to explain what's going on right here, we have my notes, but first, hydrogen absorbed onto the catalyst surface, which weakens the hydrogen-hydrogen bonds. It then allows the alkene to approach the catalyst and pick up hydrogens off the surface of the catalyst, right? So initially it's here, then the hydrogen is absorbed onto the catalyst and it weakens the hydrogen-hydrogen bonds. The alkene, right, then comes down and picks up the hydrogens off the surface. Afterwards, the pi bond, right, the pi bonds between the two carbons and breaks and is replaced by two carbon-hydrogen sigma bonds. However, what this is pretty much saying is that only 2 hydrogens are added to the overall formula to fulfill carbon's need for having 4 bonds, right? So right here, carbon only has 1, 2, and 3 bonds. However, it needs a total of 4, which is given by 1, 2, 3, 4 right here when it picks up those hydrogen bonds after that pi bond has been broken. Heat of hydrogenation is pretty much the absolute value of the enthalpy. So it's the change in enthalpy without negative charge. So again, we see that right here. The enthalpy is negative 26.9. However, the heat of hydrogenation is 26.9 kcal per mole positive. So relative stability of alkenes. What this is pretty much showing is that the most stable alkene has the smallest heat of hydrogenation, alkyl CH3. Stability increases as the number of alkyl groups attached to the sp2 carbons of the carbon double bond increases. And the alkyl groups, again, are going to be those CH3s, right? So change in enthalpy tells us the relative energy / stability of our reactants and products. And we see that right here and right here. So same product, same energy, right? They just start off at a different number. And because this one has the highest, heat of hydrogenation, it's going to be the least stable. And let me just make a quick point about this note right here. Stability increases as the number of alkyl groups attached to it increase. Right here on this carbon and this carbon, we have 1, 2, 3 total, right? And then on this carbon, we have a total of only 1 and 2. And on this carbon, we have just 1 alkyl group, which is why this is increasing in stability that way, but then it's decreasing in stability that way. And then we're again just kind of going into this a little bit more. Alkane stability increases as the number of alkyl substituents, also known as R groups, bonded to its sp2 carbon increases. So this is most stable because obviously it has the most, while this is least stable because it only has 1 R alkyl group. So we can also think of it as greater the number of hydrogens, the least stable the alkene. So alkene stability in cis versus trans. So here, down here, right, alkene stability, cis versus trans, there are 2 R groups, right? But they have different heat of hydrogenation, and that's because of the steric strain. So in this first one, it's trans, right? They're on opposite sides, and that's what makes them trans. We already went over this. So they don't interact and it stabilizes the alkene, which causes that smaller DH, right? Smaller enthalpy and smaller heat of hydrogenation, because this is the absolute value, right? Whereas these cis ones, they are right in each other's space, right? They are right next to one another, which causes high steric strain, and higher energy makes it less stable. So cis isomers will have higher steric strain and higher DH and will be less stable, while trans isomers will have lower steric strain, lower DH, and will be more stable.